Professor Mr. K. Balraj is working as a polymer consultant and teaching fellow in the area of polymer science and engineering at CEG Anna University, Chennai. He has completed AMIE in Electrical Engineering at the Institution of Engineers India, Calcutta and MTech Polymer Science and Engineering at CEG Anna University. He is also pursuing his doctoral research work in polymer technology. His area of specialization includes polymer rheology, polymer processing, characterization and testing of polymers, polymer blends and composites and insulation technology. He has in-depth experience on plastic properties, testing methods and the relevant standards. He has more than 15 years of teaching experience in polymer science and engineering, including instrumentation in polymer industries, engineering plastics, conducting polymers and rubber technology at CEG Anna University. He has guided more than 30 MTech students in their research projects. He has presented more than 20 research papers in the national and international conferences in the area of polymer science. He has published 10 research papers in the peer-reviewed journals.
Welcome to UGC lecture series in polymer science. In polymer science, we have been discussing about polymer rheology. In polymer rheology, so far we have been discussing about what is meant by rheology and the relevance of rheology in polymer processing and viscosity of polymeric melts, and then what is meant by visco-elasticity. Visco-elasticity is more specific for polymer plastics. In the last class we have discussed extensively on visco-elasticity. In today's class we will be discussing about visco-elasticity, the integral and differential approach, and then the Boltzmann superposition principle, which is an integral approach, and then Maxwell model. So these are the models which we use to explore the viscoelastic nature of polymeric materials. A quick recap on what is viscoelasticity. It is a behavior exhibited by a material that has both elastic and viscous elements in its response to a deformation or load. At this point, it is necessary to point out that viscoelasticity is not plasticity. Most of the times people think that viscoelasticity is just opposite of plasticity. It is not the case. A viscoelastic material will return to its original shape after any deforming force has been removed. Similar to a elastic material, when an elastic material is stretched and then it is left, when the applied stress is removed, it will come back to its original position, which is an elastic response. Whereas in viscoelastic material, it will come back to its original position, of course with a time delay, which is the it will take some time to do that. It is called as the viscous component of the response, which is viscoelastic. A plastic material will not return to its original shape after the load is removed. This is about a purely plastic material. In metals, this plasticity is called ductility. It is the converse of elasticity in that the energy of deformation is not stored, but is entirely dissipated. That is, in an elastic material, the deformation energy is stored. Once the stress is removed, the deformation energy will help the material to come back to its original position. Viscoelasticity is a material which can show a combination of elasticity and plasticity, in which case, although it partly returned to its original shape on removal of the load, some permanent deformation, what we call it as set, remains due to the plastic deformation, or with respect to polymers, the molecular slippage of an irreversible nature. Let us see the stress strain curves for different materials, that is elastic materials, plastic materials, elastic plastic and viscoelastic. First, the stress strain curve within a purely elastic material. In a purely elastic material, when a stress is applied, there will be a strain. Once the stress is removed, it will go in this fashion. There will not be any deformation that is permanently set. Whereas in a purely plastic material, with the increase in stress, there will be a deformation, there will be a maximum deformation, and then the flat region represents that with the increase in stress, there is no more appreciable increase in strain. Now once you release the stress, this will not go back like this. Instead it will take a path like as shown. So therefore this is the deformation which is permanently set in a plastic material, which is a typical properties of metals. Now if you look at elastic and plastic material, some of the metals do exhibit elastic and plastic effect, like with the increase in stress there will be an increase in strain. Once you remove the stress, it will slowly return to its original position, but of course the deformation will be less compared to a purely plastic material. This is because of the viscous effect exhibited by the material. Now you look into a visco-elastic material like a polymeric system. With the increase in stress there will be the increase in strain. Once you remove the stress, it will take a path, of course not the same path, but then it will take another path, but given sufficient time the strain will become zero. This is a typical of visco-elastic material, which is similar to a hysteresis effect with respect to magnetism in metals. In order to explore this viscoelastic property of the materials, particularly the polymeric melts, there are two major types of experiments which are performed. One is of transient nature, that is time varying. Another one is of dynamic nature. Now the transient experiments involve deforming the material either by applying some force and allowing the material to elongate by simple elongation, or in shear. We have earlier seen experiments for Newton's law of viscosity, that is fluid contained between two parallel plates, and then when you pull the top plate, we have seen that the top layer of the fluid getting sheared. So in either case the material is subject to some deformation, and then following the response of the material with time. So this is the transient experiments. In transient experiments again there are two different properties that are analyzed. One is creep. In one the material is loaded and then the change of deformation with time is noted. This is the creep experiment. So here load refers to the applied stress, applying some stress and then plotting how the deformation changes with time, which is called as creep. What happens during creep, particularly with respect to polymeric materials, is segments of the molecules of the material rotate and flow relative to one another at a rate controlled by the viscosity of the material. If the material is highly viscous, then the rate at which it flows is less. Apart from the viscosity, the magnitude of the applied stress and then the temperature, of course earlier we have seen temperature has a great effect on viscosity. Higher the temperature, the viscosity is less. And then particularly with respect to viscoelasticity for polymers, the time, given sufficient time, the material will relax. So the time for which the material has been stressed. These are the factors that will control the creep experiment. The curves obtained from the creep experiment, from this we will see how the strain varies with constant stress. It is also called engineering stress over a wide range of times after loading. Here a new parameter J, which is simply the compliance, which is called as compliance. It is obtained by dividing the strain by the stress and is called as creep compliance. It is roughly equal to the opposite of stiffness. If a material is more stiff, then compliance is the opposite of that. A typical creep compliance versus logarithmic of time plot is as shown. So in this we could see the different regions represent different type of flow behavior. So this is a glassy flow and this is the viscoelastic flow, which is typical of polymers. Now from the viscoelastic flow we could find the retardation time. So this is the retardation time, is the time it takes to come back to its original position, overcoming the viscous effect. And then with the further increase if you give more time, then it exhibits a rubbery flow, and then of course in the liquid the creep compliance will increase because there is no stiffness at all. So therefore with increase in time for a liquid, the creep compliance value will increase. So most of the literature data were given in terms of creep compliance for studying the viscoelastic properties of polymeric materials. The another experiment in the transient mode is the stress relaxation experiment, in which this is just opposite of creep. Here instead of stress, the material is deformed, and then the force required to maintain this deformation at a constant value is measured with respect to time. So the molecules of the material here move relatively to one another. Thus, the stress required to hold the material at constant deformation will slowly dies away with the time, and therefore the material is said to relax. That is why this experiment is called stress relaxation experiment. From the curves obtained from this experiment, we could see how the stress varies with the constant strain, and then this parameter is called relaxation modulus if it is the form of elongation, and if it is in the applied if the measured one is shear, then it is called as shear modulus. This shear modulus and then this relaxation modulus E of t and the shear modulus G of t are similar to creep compliance. This is a typical curve that gives the relationship between the relaxation modulus, that is experiment is conducted in the elongational mode, and the relaxation with respect to the log of time is shown. So, here also again you could see the different flow behaviors, the glassy behavior, the relaxation modulus of course is very high for glass, then viscoelastic, though here instead of retardation time the relaxation time is noted down, that is the time it takes so that the stress becomes 0. The stress value has to reach a 0 value or steady state value, then rubber, and of course in liquid the relaxation modulus is 0 once the time increases. The other major type of experiment or the other mode is the dynamic mode, in which either stress or strain is varied cyclically, that is it is the material is subjected to cyclic stress or cyclic strain, or in the repeated mode. Normally this is normally sinusoidal waveform is used only for mathematical convenience, and then the response with respect to time is plotted with respect to different frequencies of this sinusoidal wave. The transient experiments are generally easy to understand. So, in this today's class we will discuss about only the transient experiments. However, the assumptions made about the mechanical response of the material are similar for both the transient mode or the dynamic mode. Now, there are three major ways of describing a viscoelastic behavior in the transient mode. The first one is of course the Boltzmann superposition principle, and it is also called as the integral approach to study the viscoelastic property of materials, because it involves an integral equation. We will see that. The second way will result in a linear differential equation, which is nothing but the differential representation using assemblages of springs, which spring is an example for Hooke's law, and then a viscous element, a dashpot or damper, which is an example for Newton's law of viscosity or a Newtonian fluid. The second one is the differential approach, which of course involves these springs and viscous element as the fundamental building blocks. The third method is based on the assumption about the molecules themselves. First, in the integral model, we will see what is meant by Boltzmann superposition theory. It has two components. The first one is the creep in a specimen is a function of the entire loading history. The second one, each increment of load makes an independent and additive contribution to the total deformation. So, that is the first one. The creep behavior is simply the function of the entire loading history, in the sense whatever the material, if the material is subjected to load previously, because of that there some creep will be there, and that creep has to be added. And then for example, if you load it with 5 newtons and 10 newtons, 15 newtons, and it is similar to loading with 30 newtons, that is the second law, that is it is additive. The first condition could be called the memory function. The response of the material is influenced by what has happened to it so far. The first condition could be called the memory function, means the response of the material is influenced by what has happened to it so far, that is remembering the deformations it has been already subjected to, and then allowing them to influence its present behavior. Whatever the deformation the material is subject to already, that will have an effect on the present deformation, which is due to the applied stress now. The second condition is that if a specimen is loaded and is creeping under load, then the addition of extra load will produce exactly the same additional creep as if the total load has been applied to the unloaded specimen and the specimen allowed to creep for the same amount of time. This is said to be linear, that is directly additive response. We will see that the mathematical formulation of viscoelastic behavior derived from the Boltzmann principle is as illustrated here. For example, a stress applied like this fashion will result in a strain like this, and if you apply a stress continuously like this, then the resultant deformation will be like this, or if you apply this one first, then you observe the strain, then you apply this one, then it will be like that. So the curve, the strain curve will not start from origin, instead it will start from here, because this is the previous history or the past history or the remembering function of this Boltzmann superposition theory mainly revolves around the creep the material is already subjected to. Without getting into the further theoretical approach, the total strain at time t is given by the epsilon is used to denote the strain. It is simply given by the ratio between the sigma, which is the applied stress, by g is the unrelaxed stiffness plus. So this again, this involves an integral equation, that is why it is called integral model. So here minus infinity refers to condition before at time t equal to 0. Normally at time t equal to 0 we will start with the experiment. Here already the material is subject to some sigma, then that effect has to be taken into account. That is why the integral here starts from minus infinity to the time, and then j is of course the creep compliance, t minus tau is the relaxation time, d by dt of the applied stress, which is a strong function of the relaxation time. By solving this integral equation, one can find or one can determine the total strain at any point of time. Not only the strain, the stress relaxation modulus, it could also be calculated by using the Boltzmann superposition theory. So here the stress at any point of time is given by the stiffness, the strain plus integral minus infinity to t minus tau, which is the relaxation time. Instead of stress in the earlier one, the differential equation involves the stress. Here the differential equation involves the strain. Either the stress or the strain all depends on the tau, which is very vital because that is the relaxation time. Next we will move on to the differential method of analyzing the viscoelastic property of the materials. So the differential method involves mechanical models. Using mechanical models, that is like a spring will simulate a elastic like behavior, and a dashpot will simulate a viscous like behavior. The springs are called Hookean because it obeys Hooke's law, like metals which obeys Hooke's law, and then the dashpots are obeys Newtonian behavior, or it is compliant to Newton's law of viscosity. In the differential model, there are three standard models. One is the Maxwell model, another one is Kelvin-White model, and the third one is standard linear solid model. The first and the second one, that is the Maxwell model as well as the Kelvin-White model, do have some drawbacks. So therefore this standard linear solid model comprises of both these models. So in this episode we will concentrate only on this Maxwell model. The Maxwell model, it consists of spring as an elastic element. So likewise which is a typical example for Hooke's law, that is the applied stress is directly proportional to the strain, and then the mu is the spring constant. Next one is the dashpot. The second element is the dashpot. A dashpot follows Newton's law of viscosity. This is a dashpot which consists of a highly viscous liquid of viscosity eta. Now if you apply a stress in this direction, there will be some strain, but then the strain will be controlled by the viscous nature of the fluid. Therefore here unlike the spring, deformation will be with respect to time. Therefore instead of the strain epsilon alone, it is the strain rate epsilon d by dt of epsilon. Now the Maxwell model could be represented by combining the spring for elastic element and the dashpot for viscous element in series. This is connected in series, and now a force F is applied in this direction. First we will see the Maxwell model. The Maxwell model has two elements. One is for the spring, another one is for the dashpot. The spring will be subjected to a stress which is sigma 1, which is given by product of E suffix m, which is the spring constant, and epsilon 1 is the strain that is the spring is subjected to. And then the stress 2, sigma 2, which is the stress that is the dashpot is subjected to, which is a product of the viscosity neta m of the viscous fluid that is in the dashpot into the strain rate d by dt of epsilon 2. So, that is epsilon 1 and epsilon 2 are the strain that is experienced by the spring as well as the dashpot. The expression for spring can be divided on both sides by dt. The expression for spring that is sigma 1 equal to Em into epsilon 1, this can be divided on the both sides by dt, and then it can be rearranged and can be written as d by dt of sigma 1 into 1 by Em equal to d by dt of epsilon 1. So, this is the differential equation for spring. Similarly, for the dashpot, here the only rearrangement is required, that is the ratio between the applied stress to the dashpot, which is sigma 2, divided by the viscosity of the fluid that is contained in the dashpot. This ratio is simply equal to the strain rate that is experienced by the dashpot. Now, earlier we have seen these two elements are connected in series. So, therefore, whatever the stress that is spring is subjected to, which is sigma 1, and then whatever the stress that the dashpot is subjected to, that is sigma 2. Because they are connected in series, both the value will be same. Therefore, it could be written as sigma 1 equal to sigma 2 equal to sigma. And also the total strain on the model is the sum of the strain that is experienced by the spring epsilon 1 and the dashpot epsilon 2. The stress equations for spring and dashpot can be added to give d by dt of sigma into 1 by Em plus sigma by neta m equal to d by dt of epsilon 1 plus d by dt of epsilon 2 will be equal to d by dt of epsilon. And then in the right hand side, both the strains are additive. Therefore, we have to add the strain that is experienced by spring as well as the dashpot, which is d by dt of epsilon 1 for spring and d by dt of epsilon 2 for dashpot, and let it be d by dt of epsilon, where epsilon is the total strain experienced by both the spring and dashpot in a typical Maxwell model. In a stress relaxation experiment, the length is held constant, that is the material will not be allowed to strain. So, therefore, the d by dt of epsilon is 0, that is the total strain is 0. Hence, the total stress, this component is equated to 0, that is d by dt of sigma into 1 by Em plus sigma by neta m equal to 0. Now, rearranging this equation, taking this to the right hand side and then bringing this sigma to the denominator, or in other words expressing this equation in terms of d sigma by sigma equal to minus Em by neta m into dt. Start of the stress relaxation experiment, that is at time t equal to 0, let the initial stress be sigma naught. The initial stress in the system, that is in the model, combined the stress in the spring as well as in the dashpot, let it be this conditions, boundary conditions, we will integrate this equation d sigma by sigma into minus Em by neta m into dt. If we perform this integration with this set of conditions, then we obtain the expression for stress, which is equal to the stress at any point of time is equal to the initial stress into e power minus Em by neta m. That is, in other words, the stress decays exponentially with a characteristic time constant tau. So, this tau is the typical time constant of a Maxwell model, which is simply the ratio between the viscosity of the fluid neta m and then the spring constant em. This ratio is tau. So, therefore, using this tau equal to neta by em in this equation, we finally get sigma equal to sigma naught into e power minus t by tau. So, therefore, to summarize about the Maxwell model, it is represented by a purely viscous damper and a purely elastic spring connected in series. So, this model predicts stress that decays exponentially with time to 0 with permanent deformation. But however, this model could not accurately predict creep, that is, when the stress is kept constant, then the model fails. Therefore, here in this model the strain will increase linearly with time. Actually, the strain rate will decrease with time, whereas the strain will increase with time. Then there is a one dimensionless number called de Broglie number. It is the ratio of tau by t. This tau is the relaxational time or the Maxwell time constant, and t is the time observation time. The de Broglie number is widely used in Maxwell model, that is the Maxwell relaxation time, which is the time required to reach equilibrium after the applied stress is removed, and the t is the observation time. There is a high value of de Broglie number, then the material is more like a elastic solid. When the de Broglie value is low, then material is more like a viscous or it is a Newtonian fluid. This behavior could be easily understood with this experiment. Now, if you drop a elastic ball or a viscoelastic material, and now you give very short time, that is observation is time is very short, that is less than 1 second, then it can bounce back. Whereas, if you leave sufficient time for, if you drop that and leave it for 1 day, you could see that the viscoelastic material slowly changes its shape, its shapes get reduced, it flattens out. Eventually, that will reach a steady state like this, or in other words, if you give sufficient time, the gravity allows the system to relieve all the stress, therefore, it is more free now to flow. So, therefore, this de Broglie number is also extensively stated with respect to the Maxwell model. So, to summarize whatever we have seen in today's class, we have seen about viscoelasticity. Viscoelasticity, the integral and the differential way of exploring the viscoelastic property of the materials. One example for integral method is by means of Boltzmann superposition principle, which has two parts, the Boltzmann superposition theory. The first one, the material whatever the behavior, creep behavior it exhibits, that is influenced by the past history, that is, if the material is subjected to already some stress and whatever the creep it has undergone, that will have a effect on the present creep behavior. The second one is the additive nature of the creep behavior exhibited by the viscoelastic materials when it is subjected to a stress. Here the Boltzmann superposition principle is simply the summation of all the individual creep behavior. That is why it is well explained by the use of integral equation, which is simply summation of this creep effect. And then the next one what we have seen is the Maxwell model, which is an example for a differential approach. So, in the Maxwell model, it is like using mechanical models like a spring and a dashpot, the spring for elastic nature and dashpot for viscous nature, and combining these two elements in series, and then we perform two experiments, one for creep, another for stress relaxation. In both the cases we could find the applied stress, that is stress at any point of time, and then the strain at any point of time, and then there is one dimensionless number that is associated with this Maxwell model, which is called de Broglie number. So, higher value of de Broglie number means the material is more elastic nature, and lower value of de Broglie number means the material is more like Newtonian or a viscous nature. So, a moderate range of de Broglie value will ideally explain the viscoelastic nature of the material. Further, in the Maxwell model, Earlier I had told you the Maxwell model, and then the Kelvin-White model, what we will discuss about in the next episode, has some inherent drawbacks. In Maxwell model, it is very well suited for performing this stress relaxation experiment, whereas it is poor in predicting the creep properties. That is, if you subject it to constant stress, then the material fails to explain the viscoelastic behavior. So therefore, this Maxwell model is generally suited for soft solids with non-recoverable deformations. Viewing this episode, the viewers are expected to think of these questions, that is the Boltzmann superposition theory, what is meant by creep compliance, what is relaxation modulus, and then why this Maxwell model cannot account for a retarded elastic response, that is why the Maxwell model fails to explain the creep behavior. So these are the questions the viewers can try to answer. Thank you.